Okay, so we're gonna start on, we're gonna continue. How do I do a slideshow? Okay, so we're gonna start here. Last time we did rolling contact bearing, and rolling contact bearing is composed of this rolling component, right? The ball or the roller. Can be ball or roller. Rollers are these cylindrical pieces, right? Let me try my pen. Okay. Rollers are cylindrical pieces like this, right? They have a line contact instead of a point contact, so they have a um, bigger contact, larger contact area. That means, because pressure is F divided by A. If you have a small area, then the pressure increases significantly. That's why a ball bearing like this has a little bit less capacity than roller bearings. Okay. Different types, just different purposes. The self-aligning bearing here, it can accommodate misalignments. This is the most common, right? A double row bearing just doubles your capacity. These are some axial. Okay, so the load is this way. Okay, the load is not from the side. You cannot have that load. The thrust needle bearing here, you see it has these rollers instead of the balls. Okay, and that is for greater load capacity. And if you look at the profile, okay, the profile is really thin, right? It's really thin. So that's the significance. They call it needle because it's a very thin roller. Here's our big guy, okay, tapered roller bearing. It can sustain both radial and axial. I'm gonna hide my chat here because it's getting a bit in the way. Okay. Yeah, it's kind of annoying. Okay, so I have only my participants window open. So use audio or raise your hand and use audio instead of chat. Okay, I take back what I said before because I'm hiding my chat window. Okay, I will not see your chat. Okay, so speak with audio. Okay, tapered roller bearings. This guy, oops. This guy can take a radial as well as an axial load. Okay, you see my arrows. Okay, a radial coming from the side. That's the majority of load, by the way, right? And then some axial, and it's quite significant axial load, I can say, for this big guy. Okay, that's why you have the angle. The purpose of the angle here is to accommodate that axial load. All right, we talk about sealing. The seal is to keep the grease there. Okay, if you have oil lubrication, then there will be no seal. It's just open like this. Okay, like this, open without the seal. This is a shield. Less friction because the seal, you got some friction here. Okay, so we're gonna start talking about bearing life. Okay, again, bearings do fail. I would say all bearings fail. Okay, now the number of revolutions is the life given in the numbers of revolution. Can anybody tell me why we would specify the lifetime in revolution instead of hours? Okay, this is an open, you can just speak if you want to answer, unmute your mic. Why do you think a lifetime of bearings are given in revolutions, not hours?
Sir, maybe I think kayaknya kalau kalau bearing itu lifetime-nya tuh dari spin atau dari rotationnya, bukan dari waktunya. Karena apa namanya kan bearing itu kan muter. Kalau muter kan dia kan ada frictionnya dong. Kalau friction kan lama-lama bolanya kan bisa habis gitu Pak. Saya sih gitu.
Betul, but yeah, it will wear out. Tapi why do we specify it in revolution, not in terms of like 1 year, 1 year life? I think you're getting
Um,
somewhere though. Anybody can
ya,
also answer if you have an opinion.
Karena berputarnya tidak selalu konstan, Pak.
Okay, tidak selalu konstan. Okay, we're getting somewhere, but not exactly.
kadang bisa juga bearing tuh kita muternya cepat atau kadang kita putar agak pelan, ya betul juga sih, memang itu juga bisa masuk.
Terus kalau cepat kenapa emang?
Kalau cepat ya berarti kan dia berputarnya cepat ya makin cepat habis, tapi kalau berputar lambat kan dia pelan jadi kan nggak cepat habis gitu Pak.
Yes, very good. I mean, think about it. Kayak bohlam ya, sebenarnya ini juga kita sering ketipu kan. Bohlam bilang misalnya, oh ini bohlamnya tahan 2 tahun gitu. Well, guess what? If I turn on the bulb once a year, once a year for 1 hour, lifetime-nya berapa? Ya, maybe 100
Itu bisa lama Pak, betul Pak, karena
exactly.
kalau dimatiin kan berarti dia nggak panas kan gitu.
Exactly.
Awalnya juga nggak.
Right. So all this lifetime specification from bulbs also actually doesn't make sense, right? What they have to say is hours, not 2 years. Hours juga, it depends on the environment, but okay lah. Yeah. Now, bearings are given in terms of revolutions because it depends on, what's the speed you use it at. The faster you rotate it, then within 1 hour, you get a lot more revolution. Okay, so now rating life. Remember the C10? We talk about the C10, and the C10 is the life required for 10% of the sample to fail, probability-wise. Okay, probability-wise, after a rated life, let's say 1 million cycle, and SKF do 1 million, okay, 1 million cycle, 10% failure. Okay, so that's the catalog load rating C10. So let's say C10 is 1 kilonewton. That means if I have a bearing, okay, if I have a bearing, I give a loading of 1 kilonewton, this bearing with a C10 of 1 kilonewton, then will survive 1 million cycle with 90% probability, confidence. Okay, so that's what C10 is, a very important number because we will keep doing this. Oh, there we go. This is my slide. Okay, catalog load rating. Also called basic dynamic load rating. Okay, we got people coming up. Patrick, yeah, Patrick Fernando. Yeah, mute your video and mute. Yeah, mute your video and mute your audio. I don't know whether your video is muted or not, but no, they're disconnected. Okay, we'll keep going first. Now we have also what is called the static load rating. I think last week somebody asked about, what about static? So static is CO, okay? This is the static load which corresponds to a permanent deformation if it's heavily stressed with this load, okay? So if I have a load rating of let's say 20 kilonewton, then you hit 20 kilonewton even though not rotating, it will damage the bearing. We will talk about this later. Maybe it'll make sense later. Okay, now I would like to remind everyone about load lifetime reliability. This is what is going to, okay, somebody chat. Yeah, I don't see the chat. I guess I got the notification up there. Pretty nice. But okay. Load life relationship. This is what our equation will try to predict. It's gonna try to predict the expected lifetime of a bearing given a load. So if you see a catalog, okay, I'm gonna try to show you. Yeah, it lags a bit here. I'm gonna try to show you a catalog. Where is it? Okay, here's a sample catalog data. Okay, the bore is the hole. Okay, this bore column is the inner diameter where you can fit your shaft. So if you fit your shaft with 12, your shaft is 12 millimeters, then here's your bore. Okay, the OD is the outside diameter that you need to, you need to create a pocket to put it in, right? So if this is your shaft, right, this is going to be the bore, and the bearing will be larger than that, right? So this is the OD, and there is the ID. Bore is ID, basically. Width is the width of this. So these are just dimensions of the bearings. But then I would like to take your attention to this, the deep groove version, and here is the angular contact version. But let's not talk about angular, just talk about deep groove. Deep groove is just a standard ball bearing. That's what it is. I mean, they call it deep groove ball bearing. Now C10, okay, is the dynamic load bearing. They say dynamic because it's the rotating load, right? If it's rotating. C0 is static. We will use this for axial later on, but for now we focus on C10. So let's say you take a bearing, okay? How do I change my color here? Pointer option, ink color, okay. So let's say I'm taking this bearing, okay? Bore is 12 millimeters, OD, etc. Okay, so the C10 is 6.89. Now we already talked about what that means. Okay, so that's the dynamic load rating, meaning if I load it up 6.89 kilonewtons, it's going to survive 1 million cycle with 90% probability. But what if I say, well, my load is 10. So what is my lifetime? Okay, is it going to be more than 1 million or less than 1 million? What do you guys think?
Less than, Pak.
Of course, it's less, right? You put more stress on it, it'll survive less, right? You use a bulb more frequent, its lifetime will be shorter. As simple as that. And if my load is actually 5, then it's gonna be longer. Okay, so quite logical. So how is this load and life relationship governed? That's the question. That's what we're going to calculate is how do we do that calculation? Okay, so if I have a C10 of, kalau tadi ya, C10-nya kan 6.89. If my load is 10, then lifetime it's gonna go down. If I load it 5, then lifetime is gonna go up. By how much is the question? And here comes the equation. Okay, look at the top equation. C10 or FR and C10 is the same. Okay, FR is for rated life. C10 is catalog load rating. FD is the design load. Okay, design load FD. It is the actual load. Okay, the actual load. LR is the rated life, and most of the time, and we're just going to use this, we're going to use 10 to the 6, 1 million cycle as the rated life, because that's what is the C10 corresponding to. Okay, you see my arrows. Okay, so C10 is LR or FR. I mean, that's why we put the subscript FR. Okay, so with a load of C10, it survives LR. With a load of FD, what is LD? Okay, so that's this is how the equation works. So you have FR, FD, LD over LR, 1 over A. A is just a parameter, okay? With a load FR, I have a lifetime LR. With a load FD, my lifetime is LD. So this equation gives you this relationship, okay? This exchange relationship. We'll just do an example on this, all right? So, any questions so far about the concepts?
Belum ada, Pak.
Okay. All right, so now we're going to do an example 11-1. So here we have SKF, which rates its bearing for 1 million revolution. If you desire 5,000 hours at 1725 RPM with a load of 400 with a reliability of 90%, which catalog rating would you search in an SKF catalog? So now we have LD, the desired life or the design life, the actual life. We want it to survive 5,000 hours. But remember, there is a reason why ratings are not given in hours, because it depends on the RPM. So here goes. We need to convert 5,000 hours into revolutions. So LD is 1725 revolutions per minute multiplied by 5,000 hours. But I need to convert the hours into minutes, right? So multiplied by 60 minutes over 1 hour. If you have trouble with conversions, notice how I arrange this numerator and denominator. I intentionally do this, okay, because I need to get rid of hours. So I do the hour on the bottom like that, okay? And this minute also cancels, right? So what we have now is 517.5 10 to the 6 revolution. So we have converted the requirement 5,000 hours into revolutions. The question now, we are about to select a bearing, right? We're about to select a bearing. So you select a bearing with the catalog load rating, C10. So C10 is FD times LD divided by LR to the power of 1 over A. FD is the actual load, right? 400 pounds. We are loading it with, I don't know why we're using English units here, by the way. Anyways, okay, that's pounds. 1 kilogram is 2.2 pounds. So 400 multiplied by LD, which we calculated here. And to the 6. oops, 10 to the 6 divided by LR, which is 10 to 1 times 10 to the 6, right? 1 million. 1 over A, and A is equal to 3 for a ball bearing, okay? So A is 3 for a ball bearing, and I think it's 10 over 3 for roller, okay?
3 dari mana, Pak? Yang 3-nya itu?
It's just given, okay? I hope.
Oh,
I have it here somewhere. Ah, here.
oh. Oke.
Okay. So the A is just a constant. Okay, for ball bearings, use A equals 3. For
Tergantung yang bearing pakai bearing apa ya, Pak? Jadinya.
Right.
Itu. Oh,
right. Depends on the rolling elements.
LR juga begitu.
Kenapa?
Jadi karena ini rolling,
Yang
jadi kita
LR.
pakai 10/3 atau 3, Pak?
Ini 3. Ini ball. I believe it's a ball bearing.
Oh, ini ball. Oke, Pak.
Nggak disebut sih ya. It's a good point. Nggak disebut. Yeah, let's assume it's a ball bearing. Okay, A equals 3 for, oops, for ball. For roller bearing, we will do 10 divided by 3. Okay, so we continue our calculation. Keep touching this. Okay, then it results in 3211 pounds. Okay, what does this mean? Remember that we wanted 5,000 hours, 1725 revolutions per minute, resulting in 517 million revolutions. So I want 517 million revolutions lifetime. That is significantly more than 1 million, right? Unfortunately, you cannot just say, well, I want 517 million. What's the bearing, right? You cannot do that because the bearing catalog gives you, okay, the catalog gives you 1 million rating life, but with a certain C10. You say, I want 517 million. So 517 million, 400 pounds load. I want 570 million, 400 pounds load. So if you go to the catalog, most likely the C10 you're selecting will be greater or lower.
Greater.
Greater, Pak. Greater.
Definitely greater, right? I mean, you can, in 517, that's asking for a lot compared to 1 million. So that's what we just did. That's what we just did. We have this 3,200. So what this equation tells us is that, okay, you want 517 million at 400 pounds, that's okay. But when you go to the catalog, you definitely pick something much greater than 400. What is that number? We just calculated that with the formula. Okay? And this is all assuming 90% reliability. We have not tinkered, we have not played around with reliability yet. It will require a different formula. But for this same 90% reliability, this is the formula to kind of go back and forth. Now, there is also the probability that I give you a different number, right? I mean, I give you, oh, okay, I'm using this bearing. I want 517 million revolutions. What is the maximum load I can put on the machine, on the shaft? That is also possible. All you need to do is kind of do the mathematical manipulation to find LD instead of C10. Okay. Any questions so far for this problem?
Belum ada, Pak.
Okay. All right. So let's continue with changing the reliability now. Okay. Now it's get a bit complicated whenever you talk about reliability, because remember, reliability is all about statistics. It's not something that is very definite, right? It's probability, just like rolling a dice. So that's why what do? You do a lot of experiments. You capture the data, then you model, and turns out that it follows what is called the Weibull distribution. This is kalian belajar ini nggak di statistics kemarin?
Belum masuk, Pak.
Okay. Weibull is a type of distribution. I don't need to talk about it here, but intinya adalah we're gonna use his model. And here is, we're gonna use type 2. Okay, yeah, this is just different manufacturer. I think number 2 is SKF. Okay, SKF uses 1 million cycle as the rating life, and these are the Weibull parameters. Okay, we're gonna just stick with that, keep things simple. So, okay, let me skip this for now. I will explain it after we do the problem. Here's your formula for this. Okay, C10 now is not as simple as the before, because there is this Weibull approximation. Okay, there is this Weibull approximation. Kalau saya gerakin mouse saya, nongol nggak sih di sana?
Ada, Pak.
Ada, Pak,
Ada,
tapi kecil, Pak.
Ada, Pak.
Ada.
Tapi
Okay.
dikit.
Ada,
Okay.
kecil banget.
Okay, I'll just use my pen then. Okay, so there is this additional component. Now, XD is nothing else than just LD over LR. Okay, so when you say XD here, it's just this LD over LR. RD is the reliability that you want. Remember, D stands for desired or design. If I want a reliability greater than 90%, then I got to use this formula instead of the previous formula. FD is the same. Now, all this little guy, they are just, including B here, that's from the Weibull parameter, okay? XO is just 0.2. Theta is 4.459. And okay, ini ketutup window-nya sedikit. That's B, right? Yep, that's B. Okay, so let's just use this in the next example. This time we will want a different reliability. The design load on a ball bearing is given. An application factor 1.2. I forgot to say about that. Say something about that. The application factor AF is just a multiplier similar to stress concentration. Remember, stress concentration is a multiplication to make things worse than it is. Okay, so let's say you're doing this bearing for a sand pump for mining, then you got a lot of impact, right? That's your application factor. That's multiplying the load so that it's worse than normal. So in this question, it's given. Okay, it's given 1.2. The speed of a shaft is given, RPM. Life desired, 30,000 hours. Reliability is 90%. Okay, so here is the desired reliability. that is higher than 90. What is the C10 catalog entry to be sought? Okay, or exceeded, meaning like at least that, right? Of course, if you pick a bigger bearing, a stronger bearing, it's always okay. But here is the minimum you gotta pick. Okay, we're doing deep groove bearing, manufacturer catalog on the basis of the Weibull parameters are given. Okay, let's do this. First, we need to convert the LD, the desired life, in the form of revolution. So we have 400, again, revolution per minute, 30,000 hours, 60 minutes in 1 hour. Okay, I like to do this, 60 minutes in 1 hour. Okay, kalau kamu convert minutes to hours, then you do 1 hour on the top over 60 minutes, right? That's how I was taught to do conversions, so you don't confuse yourself. That's 720 times 10 to the 6 revolution, or 720 million. Remember we talked about this last week, that 1 million cycle is pretty short lifetime, right? I mean, in 1 month, just by 8 hours operation, you can easily exceed that. Easily. Now, for this new formula, I don't have the formula. Here. There is XD. So, I gotta do XD, which is just LD over LR. 720 million divided by 1 million. That's easy. 720. So you can think of this XD as just a multiplication of the rated life. So if the rated life is 1 million, then my desired life is 720 times, right? 720 times the rated load, or the rated life. So if the lifetime, you know, the kind of the standard lifetime is 1 million, I want 720 times that. That's what XD is. Okay, you can think of it that way, supaya nggak bingung. Okay, now we go to the big formula here. C10 is, remember, AF, which is 1.2. I'm not gonna rewrite it, yeah. You can always go back to the, remind me to share my slides later. I keep forgetting to do that. Okay, I will share the slide later. Okay, application factor is 1.2. It's given in the problem, okay. Times FD. FD is 1.84 kilonewton. Okay, we're doing all this in kilonewtons. XD is 720 on the numerator. This is X0. This is theta minus, I'm sorry, theta minus, why am I doing this different? That's theta minus X0. 1 minus 99%. That's B. Again, these all comes from Weibull. Okay. This formula, we got theta minus X0, 1 minus RD, and then 1 over B. And the whole thing is ada pangkatnya, dipangkat 1 per A, sama seperti formula yang tadi ya. So you have 1 over A, again A is equal to 3, This time we're given ball bearing, see on the problem set, 1/3. And C10 then is 32.8 kilonewtons. This is the catalog rating we need to look for if we want 720 million lifetime under a load of 1.84, which is kind of multiplied. This multiplier 1.2 make it worse. Okay. Any questions on the calculation? Okay, if there's no question, I'm gonna summarize this again, right? This desired, we want 720 million revolution, 1840 Newton or 1.80 kilonewton, 99% reliability. That's the requirement. That's what we want. But remember, the catalog always gives you 1 million lifetime with a C10, right? That's the given. And the C10, if you recall, the definition, by definition, C10 is 90% reliability. We figure out this guy turns out to be 32.8 kilonewton. So my actual load is 1.84 kilonewton. Why do I need to find this? Well, because first of all, you're asking 720 million instead of 1 million. More than that, you're asking for 99% reliability. So we end up 32.8, and there is an application factor 1.2, which we did multiply with 1.84 to make it require something even more. Okay, any questions?
Pak, boleh slide-nya dimundurin sekali nggak Pak? Yang tadi kerjain soalnya. Nah ya, lihat dulu Pak.
Again, we can also ask the question the other way, right? This is called a design problem. In a design problem, you're given a requirement and you need to select a bearing. But in a different situation, you might be given a bearing, but you need to analyze what's the lifetime of it. In that case, then XD here will be the unknown, right? The LD, the desired life, will be the unknown if I'm already analyzing a specific bearing. That can also happen.
Pak, bedanya rumus ini sama yang tadi itu cuman buat reliability doang, Pak?
Iya.
Kalau misal
karena dia minta reliability yang bukan 90%.
Kalau diminta di bawah 90, Pak, misalkan kayak 70, 80 gitu, pakai equation yang
Nggak ada. Karena 90% is already very, very low.
Oh, jadi bakal ada kalau nggak 90, pasti dari 90 doang gitu, Pak?
Betul. Makanya kamu lihat di sini, R is greater than 90%. And it is very unlikely that we are looking for less than 90%. It's just not practical. Okay? Any other question? If we do have multiple bearings, like 2 bearings, remember a shaft more than likely is supported that you have 2 bearings here and here, right? If you have 2 bearings, then if one of them fail, consider that failure, right? So statistically, when we have reliability of A and reliability of B, the combined reliability is RA times RB. Okay. Why do we not do RA plus RB? A little bit of mathematics trivia here. If I have two bearings and none of them can fail, why do I do multiplication and not addition? Anybody wanna take a shot?
Mungkin itu Pak, kalau misalnya satu bearingnya rusak, yang bearing satu lagi bakal kena juga Pak. Itu kemungkinannya sih Pak.
Betul, tapi mathematically kenapa kita do multiplication instead of addition?
Karena peluang, Pak.
Keep going.
Kalau probability memang gabungan dikali, Pak. Karena nggak masuk akal kalau dijumlah, Pak. Misalkan dia yang satu 0,9, satu 0,9. Kalau dijumlah langsung 1,8 dan itu kan nggak mungkin kan. Karena istilahnya dia main persen. Di atas 100% itu istilahnya 100% gitu. Seharusnya kalau dua barang tidak sempurna digabung.
Mathematically I can see your point. Think about logic. Is this an and or an or?
And.
Because bearing A and bearing B has to survive, right? And it's an and. If it's an and, you do a multiplication. If it's an or, you do an addition. Now you cannot do addition for reliability probability, but you have to do it for failure probability. So let's say my failure probability is 10%, right? Let's say 10% for this and 10% for this. The question, what is the probability that one of them fail? It's an or, right? So you add them. But if it's an and that both of them fail, you multiply. But here we're talking about the reliability percentage. So the reliability, both has to be reliable. So it's an and relationship. It's a multiplication, okay? So if you have two bearings, they're identical. So you have to multiply them and say you want the total reliability. I'm going to pause a little bit here. My internet, it says unstable. Are we good? Okay. We're back, yeah? Okay. So let's say your boss wants 99.9% total reliability. Then this is the total, and if it's identical, then you have to make sure they are the multiplication of them is 99.9, so each one of them has to be a square root of it if you have two bearings. Okay, when you go to bearing codes, they are standardized by dimension. Okay, so let's say a 0, 1, 2, 3. By the way, I like the red ink better. Okay, let's say you have 0, 1, 2, 3. That's the width series. And there is the dimension series. There is the diameter series. So your bearing code will be a combination of this, and the first digit designates the width, second digit designates the diameter, and then so forth. Just in case you're wondering why it's always specified that way. Okay, I'm gonna clear this pointer option, erase all. Okay, So here is a typical catalog, right? Remember, we look at this C10. Obviously, the dynamic load capacity goes up as the bore goes up. So bigger bearings have bigger load capacity. Should be obvious, but you know, that's how it is. This is roller bearings, okay? Again, O2 series means the width, yeah? This is the width. Now, what if we have a combined radial and thrust loading? We will have to go through a procedure to combine them. Okay, remember there is a question in the quiz. If you have a combination, let's say this is the bearing, okay, you have radial and then you have axial. How do you combine FR radial? Probably shouldn't call it FR. Let's see, what do we call it here? Yeah, FR, small r. Okay. Small r, FA, which is axial. How do we combine these two? Well, the answer is not as straightforward as you might think, because we have to do a procedure to find out how big of an influence is this axial force, okay? How big of it will influence depends on some ratios. So I have I have created a slide that gives you a step-by-step approach to evaluate whether FA will influence it or not. Okay, first you calculate this ratio. Second, you calculate this to compare with the E. This is the E. Okay, so first you calculate FA divided by CO to look up E. Second, you calculate this quantity and compare it with E. Depending on inner or outer ring rotation, the V will be different in this formula. If you have a bearing like this, okay, let's say you you have a shaft. On it, you have a pulley, and the pulley is being used to lift something. Oke, ini kayak problem fisika deh ya. Oke, ini langit-langit. Oke, ini ada katrol. Saya lagi angkat ember, isinya semen. Oke, ini outer ring rotation atau inner ring rotation? Ada yang mau jawab?
Outer ring, Pak.
Kenapa?
Soalnya yang di luar yang muter, Pak.
That's what it means, outer ring rotation, yang luar yang muter. Karena puli ini masuk kenanya ke outer ring, ya kan? Kalau ini bearing,
karena pulinya diem. Karena pulinya diem. Kalau serinya dia bearing kan berarti yang luarnya yang diem, yang dalamnya yang gerak.
Oke, kalau kita lagi ngerek sesuatu, ini kan bearing nih, ada inner, ada outer kan? So when the pulley is mounted, it's mounted on the outer. Okay, so when the pulley rotates, the outer surface of the bearing rotates. Compare a different situation. Let's say you have a motor spinning a shaft, and the shaft is supported on a few pillow blocks or 2 pillow blocks, right? And the pillow blocks are mounted to the table. So there are 2 pillow blocks like that. The shaft connects to the inner or outer?
In
To the inner,
Inner, Pak.
right?
Inner, Pak.
So that's inner ring rotation. Okay. So situation like a shaft turning on a static pillow block would be inner ring rotation, but situations like a pulley will be outer ring rotation. So this is how you determine V. Here's your table. Now the table gives you a relationship between FA over CO with the E, and then based on that, then we will have X1, Y1 to give you a relationship between the axial and the radial, okay? You notice that if it's less than E, if it's less than E, then the axial, which is Y1, basically axial has no effect, okay? This is what means that I can ignore my axial component if it's less than E. If it's greater than E, then I will combine it this way. Okay, so we will do this calculation problem. Let's take a quick break here. Yeah, so, oh my pen. 400 and a radial load. Okay, that radial load given 500. So we're gonna have to combine these two. We're given that the outer ring stationary. Now at other times, I might, instead of giving you outer ring or inner ring rotation, I might give you what is stationary, or I might give you a situation and you have to interpret whether it's inner ring or outer ring, okay? You're given the basic static load rating. Remember C0? Now this turns out to be used in the axial radial combination. C0 is given, C10 is given. We are about to estimate the L10 life at speed of 720. L10 is simply LD with 10% probability of failure. Okay, so it's really the question asked for LD. Okay, assuming 90% reliability. So L10 means 10% failure probability, means 90% reliability. Here we have the original formula, but before we use that, this guy has to be replaced with what is called an equivalent load. This is the equivalent. This equivalent will be a combination of radial and axial. How we combine them is the big question. So we're going to do that next. The first step in combining this, first of all, let's write down everything that we're given. Yeah, FA is 400 pounds. FR is 500 pounds. C0 is 4450. Again, these are the givens. What you're looking for is not selecting a bearing this time, but this time we are analyzing an existing bearing. Okay, we are given that outer ring stationary, so that means inner ring rotation. So V is equal to 1. Okay, if outer ring rotation, V is 1.2. So the question is estimate lifetime at 720 RPM. Okay, I think we have everything written down. So the first step is to calculate FA over C0. And we're going to use this to look up E. Okay? Here is a table where we will look up E. First, we calculate FA divided by CO. So FA divided by CO is 400 divided by 4450. Remember, CO is the static load rating. Here is a typical table, remember? You got the C10 and you got the CO. Okay, CO is the static load rating from a catalog. Okay, FA divided by CO is 0.09. E then, you know, FA divided by CO is 0.09. It falls somewhere here. Okay, somewhere between 0.084 and 0.110. The E is somewhere between 0.28 and 0.30. We have to do what is called an interpolation because we want to know what is the E in between. Okay? Remember interpolation? Interpolation is when you have 2 points, right? We're going to assume it's a linear relationship. And the question is, if I'm here, what is my Y, right? So this is called an interpolation. We have this point and we have this point. We want to know what is in between, the value in between. So here is 0.09. So we're going to interpolate. E is 0.28 plus, if you don't remember this, review your math, algebra, whatever. Times 0.09, 0.084, 0.285. Now, whether you will interpolate or not, it kind of depends, right? Sometimes you know for sure, like what we'll do on step 2, right? Calculate. You know for sure that it's going to be greater or less than E, so don't bother. You can do that. Okay, the second step, you calculate FA divided by VFR. In a sense, this is like the ratio, right? It's somewhat of a ratio. You know, how big is this axial guy compared to FR? Calculate this, 400 divided by 1 inner ring rotation times 500 is 0.8. It is greater than E. Okay, the second step is you calculate FA divided by VFR, which is 0.8. You compare it to E, definitely greater. Again, what I said, whether you need to interpolate or not, if you kind of go ahead and do step 2, even the largest here is 0.3, right? So you actually say, you know, forget about interpolation. I mean, even at FA divided by CO here, it's 0.3. And so my FA divided by VFR is definitely greater than even 0.3. So forget about, you know, I don't need to interpolate. So you can do that, okay? Because it's greater than E, then we're going to use X2, Y2 in the table. Okay, I'm gonna change color here because there's a lot of red already. Let's do blue. Okay, So if it's less than E, we're going to use x1, y1 in this. And if it's greater than E, x2, y2 is given. Okay? So now we're going to then proceed, use x2 0.56, y2 is 1.527. Now this is x 0.56, you don't need to interpolate, but y2 you do need to interpolate, right? Because they're different. And our FA over CO falls in between this table. So unfortunately, you do need to interpolate here. Not much choice. So this is interpolation. Okay. FE then, the equivalent, which is the combination of axial and radial, we will combine it this way. X2 VFR plus Y2 FA. Notice X2 and Y2 is basically a multiplier, right? It's kind of like the weight. Y2 multiplied by FA, X2 multiplied by FR. So if you use this instead, let's say it's less than E, if Y1 is 0, what happens here? If Y, the multiplier to FA is 0, what happens is basically we're ignoring the axial part, right? But here, because the comparison gives us this FA divided by VFR is greater than E, therefore, it needs to be taken into account. That's what it means. So X2, 0.56 times 1 times 500 in a ring rotation, 1,527 times 400. Okay, the combination here is 891 pounds. Again, this is the equivalent load. So we can go back to this original equation, and instead of putting the radial load on the FD, we're gonna put the equivalent load that we calculate. So every time you have axial and radial, you have to calculate. I'm not gonna put plus here because some of you might thought it's addition. Okay, it's not addition, it's a combination. Calculate FE. I cannot stress how often students miss this. They see axial and they see radial and they just add them up, or they just use the radial. Happens all the time, no matter how often I emphasize this. You need to do this procedure before you proceed with this equivalent number, 891. Okay? The rest will be similar to what we did before. So before I move further, any questions on this combination? No questions? Okay.
Pak, itu hasilnya 89,1 ya, Pak? Atau 891?
891.
Oh, 891. Ya, makasih, Pak.
Yeah. I buy a cheaper stylus here, so okay. All right, we will proceed with the live calculation. Same formula, C10 equals FD, LD, LR, 1 over A. The difference now is that we're not looking for C10, right? We're looking for LD. LD is LR C10 over FE. Well, I'm skipping some steps here. Let's do this step by step. Okay, I want LD, right? I want LD. So we are going to try to get LD out from the equation. I'm gonna take a power of A on both sides. Well, actually, I'm gonna move this guy here first. Okay, so C10 divided by FB equals LD divided by LR 1 over A. So I'm gonna do a power of A on both sides, right? So if I do power of A on both sides, we end up with C10 over FD to the power of A, LD over LR to the power of 1. So move LR over here. I end up with LD equals LR C10 over FD to the power of A. Remember what is FD? It's basically the equivalent load. I cannot just use the radial or the axial. I use an equivalent load. So I end up 10 to the 6 is the LR C10 over FE to the power of A. So now we have 10 to the 6. What is C0 again? 7,900. 891 to the power of A. Now what I will get is basically a number of revolutions. But I believe, or cycles, right? Revolution or cycles. 8.87 million cycles is the survivability. But I think it's asking for number of hours. Yes, that weird little L there is in hours. The capital L is in it's in cycles. So let's do a quick conversion live in hours. What should I do? Any suggestion? How do I do this?
Divide by RPM.
Divide by RPM. Okay.
And then divide again with 60.
Okay. Explain why I divide by RPM.
You divide with RPM to get the minutes. And then you just need to convert it to hours.
Okay. Because this revolution happens multiple times and it's given by the RPM, right? So how many hours will depend on the RPM, but because I want to scratch out RPM, right? I actually do a division. So I'm doing 720? 720 revolution in 1 minute. That's how I write it. So you don't have to memorize whether you divide by RPM or multiply. Think about it. I want minutes. I don't want revolution, right? I want minutes. I want time, basically. I want time. Oops. This thing is messing up. Okay. So here I want it in terms of time. So I have 60, 60 minutes in 1 hour, right? Okay, you see what I'm doing? I
Pak, itu
want
A-nya
hour. Kenapa?
kayak ada salah hitung, Pak. A-nya 3 bukan, Pak?
Iya, hanya 3. Salah hitung ya?
Iya, saya dapatnya itu bukan 8,87 tapi 697, Pak.
600?
97.
Okay. Thank you. Don't know why I'm way off here. LD. Yeah. Okay. Can you do the math on the number of hours then?
Okay, wait.
While you do that, I'm gonna keep explaining this conversion because this might not come as intuitive for people. Now I'm telling you, I'm not that good in math. In fact, this is something I discovered helped me because I cannot memorize whether I divide by RPM or I multiply. So what I do is this, I basically say, well, I have revolution or cycles, right? Here, cycles also means revolution. I want it in hours, right? I have revolution, I want it in hours. Well, I need some things here. I need the RPM, but RPM is RPM, revolution per minute, right? But here, if I multiply by RPM, I got revolution square. So I want minutes. I put the revolution upside down. Therefore, my revolution cancels. So now, revolution cancels, I got minutes. I'm not done. I want hours. So, do I multiply or do I divide? Again, I would think I want to scratch out minutes. So I need to put minutes on the bottom, right? Because here minutes is on the top. So I want to pass out minutes like that. In 1 hour, there are 60 minutes. Nathan, can you mute your mic? Okay. In 1 hour, there are
16 kilo hours. 16 kilo hours.
Okay.
Oh, itu it should be 997. 697.
697.
Yes. Okay.
All right, thanks. So my final answer is correct. Somehow I got that cycles messed up. Okay, so again, I want hours. So I multiply with 1 hour over 60 minutes. There are 60 minutes in 1 hour. Again, these are elementary math, but it can mess you up real bad in an exam. Okay, so you divide. Okay, any questions on the conversion?
Apa itu yang 720 tuh dari mana ya, Pak?
RPM. It's you see the problem statement here. The question asks you estimate lifetime at a speed of 720. Any other questions? Okay. No questions. All right. We discussed some of these already. Here is a table of load application factors. So you can back to red here. So these are the load factors. You see the determining factor is precision gearing, commercial gearing. If your gearing is not as precise, you know, there is some vibration due to the gear not being smooth. Poor bearing seals, machinery with no impact, light impact, moderate impact. This is all a range, I guess. So again, it's, you know, an engineer estimates, right? That's we do estimation. If you feel, no, this is really bad, then you take the upper limit. These are just some bearing life recommendation. The number of hours here with certain reliability that you want. Lubrication, we did this, right? Grease versus oil. Bearing mounting, pillow blocks, yep, duplexing, fits. Okay. Usually when you have, when you want to do a press fit, let's say you have a shaft. Remember, if I put a bearing block here, what is rotating, inner or outer?
Inner, Pak.
The inner part is called the rotating ring, right? The rotating ring. The rotating ring is usually a press fit. Now this is to prevent any loosening that might happen on the rotating component. So the rotating ring is usually a press fit. So in this case, the shaft should be a press fit to the inner ring. The stationary ring in this case is the outer ring, right? It's stationary and it can do with a push fit. So in this case, the bearing is a push fit to the pillow block, but it's a press fit to the shaft. Okay. This also allows the stationary ring to creep, bringing new portion into the load bearing zone to equalize wear. So it's going to expand when it gets heated up, and over time it also creeps, right? It lengthens. So you allow some expansion in the stationary ring. This will give you a longer lifetime. So in the opposite, right? Let's say there's a pulley. Remember, you use a pulley to lift a load, for example, like a winch. This is mounted to ceiling. The opposite is true here. The outer ring rotates, so that should be a press fit, and the stationary ring with a push fit or a looser fit. Alignments, yep. Okay. Any questions on bearings, rolling contact bearings? Let's go to bushing a little bit for the rest of our time. I'm gonna postpone the Socrative pretest maybe for the next session. Okay. I want to play some video actually. How do I do this? Wait a minute. Can I copy paste? Huh. I wonder if I can play videos here. Let's see.
Bapak screen share aja, Pak.
Iya sih. But let me first show some images. I'm surprised my PowerPoint slide doesn't even have images of bushings. So let me share my Chrome. Oke, sekarang yang saya share Google Chrome kan ya?
Yeah.
Nah, so this is a bronze bushing. Okay, they use bronze because it's worn out. I mean, it's low friction for to start with, but then you can wear this thing out, right? It's softer metal than your shaft. So when the shaft rubs against this bronze bushing or brass itu kuningan ya, bronze itu perunggu. This thing wears out, right? Yang kemakan bukan shaftnya kamu, yang kemakan itu bushingnya. Karena ganti shaft jauh lebih ribet daripada ganti bushing kan. Sometimes they have this lubrication hole. Yang ini kalian lihat ya, ada splitnya. Ada splitnya. Lalu di sini ada groove-nya. Okay, there is this little channels for the oil to kind of flow. So you do lubricate this. See, there are sometimes these channels for the oil to kind of circulate. Sometimes you have some graphite. Here is a bushing with some graphite on it. Titik-titik hitamnya ini carbon, just like your pencils. The graphite is actually very low friction. Do some Googling a little bit sometime. Graphite is a very, very low friction material. Licin sekali. Ya, jadi kadang mereka combine between bronze to provide the strength because graphite is very fragile. So I mean, you cannot just have full graphite; it will crumble literally. I guess they do make it, but it's very fragile. I'm guessing most likely they kind of put some powdered metal also to strengthen it. Okay, like these graphite bushings. But most of
yang bushing itu ya, kalau grafit itu kayak gampang hancur gitu ya Pak?
Ya, grafit itu kayak pensil kamu lah. It's easily broken, right? Jadi dia ditaruh sebagai additional material, tapi the structure is bronze. The structure itu lebih kuat gitu. So these are bronze graphite, basically. Graphite impregnated bushings, right? Yeah, bronze, brass, they look similar. But then you got the plastics. The plastic bushings, you know, ini bukan bushing dalam arti bearing ya. Yang ini salah nih ya. Ini bentuknya seperti ini sebenarnya. Okay, or this. By the way, bibirnya ini mau saya kelihatan nggak ya? Okay, let me see if I can annotate this. Nope. What did I do? I think I clicked it. Ya, bushingnya ini ada flange-nya ya, flange-nya. Annotate, okay. Alright. Nah, ini bibirnya ini namanya flange. Tujuannya adalah untuk dia duduk. Jadi kalau misalnya ini shaft, ini ada hub gitu ya. Waktu kamu taruh bushingnya, bushingnya kan mesti duduk. Nah, kalau dia nggak ada flange-nya ini, nyeplos kan, dia jatuh gitu. Oke, so jadi bibirnya ini, oke, this flange itu buat duduk. Oke. That's a plastic bushing. Now, these plastic bushings can be made out of nylon. Ada satu material saya lupa namanya apa ya, polyethylene, UHMW plastic. Okay, this thing ya, this thing are pretty low friction also. Polyethylene, okay, ultra high molecular weight polyethylene. They are quite low friction, so you can use this as bearing materials also. If you want plastic bushings. Okay, so these white ones are often made by these polyethylene bushings, nylon, Teflon is also low friction. Okay, it's the same thing as you have in your panci-panci, yeah? Slow friction. Those are some ceramic, yep, it's fragile though. Biasanya ceramic bushings, I don't see that often, but sometimes you have it in ball bearings, okay, but you have ceramic rings. They are very hard, so it's very low friction. So the inner and outer race itu made out of ceramic. The balls are still steel, ya, tetap baja bolanya. Tapi ring dalam sama ring luarnya itu terbuat dari ceramic. So there are ceramic ball bearings, very strong, very accurate. Tapi kalau bushing kayaknya jarang ceramic. Ya, bushing kebanyakan Teflon karena this thing literally rubs. Okay, it rubs on the surface. That's why our calculation, okay. Okay, I need to change the screen sharing again. Back to PowerPoint. Yeah. Okay, that's why the model here is a sliding wear. Okay, linear sliding wear. Because if you have a bushing like this, okay, kan dia sliding di sini nih. Okay, the shaft basically rubs on this. But if you take an element there, it's basically like having a block and then you slide it over a surface. Okay, you just push this thing across. Okay, it's like rubbing. So this is a sliding wear. Here's some bushing material. Wear factor is how fast it will wear, how soft it is basically. You got nylon, PTFE is Teflon, some combination with glass fiber maybe to strengthen it a bit. Not sure what this MOS is. I think it's molybdenum. Molybdenum, yeah. Okay, got polycarbonate. Most common is just nylon, Teflon. Bronze, yeah, bronze, porous iron. Phenolics is a type of plastic. Nylon, Teflon, Delrin. Delrin, I think it's a trade name, a trademark by a company. They develop a special. Okay, carbon graphite. Yeah, rubber, wood. Obviously, you don't actually want them as real bushings, but it's there. I mean, sometimes it shows up. Here's a typical sliding friction coefficient here. So with a bronze, you get 0.03. I don't know. That seems too low. probably more like 0.05 or 0.1 even in reality. The thing is with these guys, you know, you gotta have it really clean, okay? It's gotta be clean because remember, they are rubbing. So if you get anything between the shaft and the bushing, it's gonna, itu udah kayak diamplas, okay? So if you have dust coming in between the shaft and the bushing, and remember, I mean, it's rubbing, and if it's a high RPM, you know, you rub a lot of this, and the dust literally becomes your abrasive, and you're gonna wear out the bushing very fast. We're gonna do some equation, not today, but what happens here is that you got pressure and sliding, okay? Pressure and sliding. So depending on this maximum pressure, the velocity, and the combination of pressure and velocity, you're gonna wear out your bushing, okay? So basically you have maximum, so bushing design involves maximum pressure limitation, maximum velocity, because some bushings cannot tolerate too high of an RPM. In fact, most bushings are not tolerate, does not tolerate a high RPM. And then you got combination of P times V. And in a way, P times V is like the power, right? It's like power because P is pressure from force, and then you have velocity sliding. Force times sliding equals power. Okay, so this is kind of like the amount of power being transferred, or heat, right? I mean, this is heat. This heat generated on the bushing. You know, bushings are very, very useful. I mean, you might have applications where you don't have high RPM at all. I mean, think about linkages, for example, right? So let's have you have a block, and then you have an arm that just needs to rotate back and forth, right? Your wiper, for example, I mean, just back and forth. It's not like you're spinning for 1,000 RPM, right? It's not. Nothing like that. It's just, you know, low RPM, back and forth. You just need a sliding surface. So anytime you have low RPM and low duty cycle is what we call it, right? Low duty cycle. What duty cycle means is, you know, the difference between a household vacuum cleaner and an industrial vacuum cleaner. A household vacuum cleaner, you use it like once a week for maximum 1 hour. Industrial, you can use it for 8 hours a day, 30 days a month, okay? That's the difference, is duty cycle. So low duty cycle, low RPM is bushing. Go with bushing, not ball bearing, okay? Ball bearing, you need to be very accurate. Alignment, it's just a pain. Use bushing, and you will see like later in your MSD projects, whenever you have movements, I want you to use bushings. You need to have a smooth sliding surface. Use bushings, and when you have high RPM, constant rotation, then use ball bearing. Okay, I think that's as far as I want to get with bushing. Let's see, what else do I have here? Yeah, the rest are mainly calculations. Yep. Okay. Any questions on bushings? Practical design questions, maybe? Ever seen it? Or any one of you experience it?
Pak Leo.
Ya.
Emang kalau bagian inner ringnya apa? bagian dalamnya bushing emang harus clean, bukannya dia harus ada kayak kasar-kasar sedikit, Pak.
Harus kasar. Kenapa harus kasar?
Kayak ada kayak kasarnya fine gitu, Pak. Kayak hampir fine polish. Kayak fine gitu lah, Pak.
Not really. The smooth, kalau kasar dia bakal usually worn out pretty soon. Lalu nanti setelah dia halus, dia tahan lama. Jadi kadang-kadang bushing kalau masih baru, dia ini. Bushing kalau masih baru, coba saya gambar ya. Misalnya inner surface ini grebesan gitu ya. Okay, this thing will be shaved off once you use it, and once it's smooth, then it's gonna be long lasting. So no, you don't want any surface yang grebesan gitu inside of a bushing. By the way, most bushings it's inner rotation ya, bukan outer rotation. Yep, usually. Any other questions? Okay, well, I will assign homeworks. We're so behind on homeworks. Tapi kadang-kadang saya mesti cari homework yang tepat karena we skip so many subtopics. I mean, kalau kita follow all the topics, it's gonna take a long time. I need to compress my syllabus. But this one I can assign you something. Oke, jadi bakal ada homework ya. Oke, kalau nggak ada apa-apa lagi, I will save this. I will save this file. I will share my. Okay, let me make a note to myself before I forget.